we had determined that our standard widths on all of our 5 rectangles was going to be 2/5, and so we were going to find out what our heights were. Our heights are determined by where our rectangles intersect on those upper left corners the curve y equals x squared. So if we start with an x value of 0 and we go a distance over of 1 width, we know that along the x-axis this is the value 2/5. So if I was to put 2/5 into the function y equals x squared, that would give me this value right here, the height of that rectangle, the second rectangle there. The height of the first one is clearly 0, but this would give us the height of the second rectangle, because when I put 0 into the function y equals x squared, I get 0 squared. So let's just do that. We're going to come down here and we're going to plug those heights into our function, which is our x value squared. So we know all of those heights are going to be wherever we are here along the x-axis that the height is coming from for that rectangle, all the left sides of those rectangles. So for the first height, we said that our input value here that is giving us the height of our function is to put 0 into our function. So that's 0 squared. So here is our width and here is our height, okay, for our first rectangle. For our second rectangle, which was right here where I started, we're going to put 2/5 into the function y equals x squared, and that's going to give us the height of that rectangle. For the third rectangle, we need this value right here along the x-axis. Well, this is 0 plus 2/5. Every width is another 2/5. So 2/5 plus 2/5 is 4/5. So if I put 4/5 into the function x squared, then the height is going to be that x value, which is 4/5 squared. And as you can see, this is going to be 6/5. This will be 8/5. And down here at 2, which would be 10/5, or 2, we can see that we're on track here. Now, the next height for this rectangle, for our fourth rectangle, comes right here from this x value. So we're going to plug that into our function, and our last and final rectangle gets its height from its upper left hand corner, so we're going to put this value into the function. So there are all of our heights. There are all the individual heights. Now the area can be best approximated by adding all of those together, that's what that would look like. So algebraically, let's look at what this looks like. Every one of these heights has the same width. Every single one of them has the same width. I can factor that out of areas. Every single one of them has a width of 2/5. So what's left is 0 squared plus 2/5 quantity squared, plus, there's height 1, height 2, because here's the width, and it's the width times the sum of the heights that I'm getting now. And that's going to get me the same value, all right? So I have 4/5 squared plus 6/5 squared plus 8/5 squared. And you say, well, you didn't use 10/5, you didn't use 2. No, I didn't, because this is the value it would give me, and that's not the height of any of my rectangles. So when I'm using left upper corners only, or left endpoints, I'm going to start at the leftmost endpoint, but I'm not going to be using the right endpoint. So I'm not going to take time to actually analytically find a number for this, but you could find whatever that number is, get your calculator out, or find your common denominators, whatever you want to do. But if this was a free response question, this is all that I would need to show, because this is the sum of the areas of those 5 rectangles. So we're beginning to see how we could approximate the area in the plane using left endpoints, right endpoints, and we'll see here in a minute we could even do it with midpoints. So let's work this example. Approximate the area in the plane between y equals x squared and the horizontal axis. Again, here's the horizontal axis is coming right out here. There's the x-axis. From x equals 0 to x equal 2, again, we're using 5 rectangles. We have area 1 and area 2, area 3, area 4, and area 5. But now the heights of our rectangles are coming from the upper right corner. They're coming from the upper right corner, or the right end of our widths along here. So our widths are going to be the same as the last example. This is the same function. We have the same standard widths. It's the right endpoint minus the left endpoint divided by the number of rectangles. So our widths are a standard 2/5. So now I'm just going to say the area is approximated by, because my widths are common to every rectangle up here. Now all I have to do is write the sum of the heights. So I need height 1, which comes from right there, and height 2, and height 3, and height 4, and height 5. Notice that now my heights, I don't start at the left endpoint. This is going to be the height of this first rectangle. This is the height of the second rectangle, and so forth, because it's all coming from the right side of my rectangles, not from the left side of my rectangles. So we said before that this was 2/5, and another 2/5 over was 4/5. We said this was 6/5, this was 8/5, and of course the very right endpoint was 2. So the sum of my heights is plugged into my function. My function is y equals x squared, right? That's where the height comes from. These y values are going to be found over here by plugging those input values in to the function y equals x squared. So height, my first height, comes from plugging 2/5 into the function. That's height 1. My second height comes from plugging 4/5 into the function. That's height 2. Here's height 3. Here's height 4. And finally, here's height 5. And again, I'm done. That's a real number value. I don't have to simplify it or clean it up. If it's a free response question, I need to learn and be comfortable with just walking away that this is an approximation for the area trapped in the plane under y equals x squared from x equals 0 to x equal 2, below the curve and above the x-axis. So that's what right endpoints or right upper corners would look like. Now, let's finally do this one. I don't know if this is the last one, but let's do midpoints. We're going to approximate the same area in the plane between the same function over the same interval using the same number of rectangles. And now we're going to use the upper midpoints. That's what lies on the curve. There's the midpoint of our rectangle. There's the midpoint of our rectangle. Midpoint, midpoint, and midpoint. This is still function y equals x squared. We still have the same interval, the same number of rectangles. So once again, we don't have to do this work. We've already done it. We know what those values are. So our area can be approximated. Again, all of our rectangles have the same width. Now we just need the sum of our heights. Well, our heights don't come from the right or left side anymore of our rectangles. They come from the middle. So what's halfway in between 0 and 2/5? If I want half of 2/5, well, that's 1/5. So this first height of our first area comes from plugging that midpoint value, which is 1/5, into the function y equals x squared. So there's our first height. Our second height comes halfway in between 2/5 and 4/5. And not surprisingly, that's 3/5, right? So we're going to plug 3/5 into our function. And the next one is 5/5 or 1 into our function. The height 4 comes from halfway in between 6/5 and 8/5. That's 7/5. Oh, and we need to square it. And here would be 9/5. So it doesn't matter whether they tell us to approximate the area, and again, please use that tilde because it is an approximation. You can clearly see it's not an exact area. We have just as much of an under approximation as we do an over approximation. So it's not exact, but it's close. And so we're going to approximate the area by taking our standard widths. And again, I want to reiterate, not every time we do this are the widths going to be the same for every rectangle. But if they are, then this is a way to do it. We have our widths times the sum of our heights, how many ever heights we have. Here we had 5 of them. So that's going to get us the same area as if we did them individually. This times that, plus this times that, plus this times that. We're going to get the same thing. Here's one final example. We'll see if we can get through this. And notice this time they don't have a picture for me. Well, you know what? That's perfectly okay. I don't need a picture every time you ask me to do this. This says to approximate the area in the plane between y equals x cubed, there's my function, y equals x cubed, and the horizontal axis, so below the curve and above the horizontal axis, from x equals 0 to x equals 4, using 8 rectangles and midpoints. So here's how we do this. Let's draw the interval in the plane. Here's 0 and here's 4, and I need 8 rectangles. So let's just kind of sort of split everything in half as much as we can. There's 8 rectangles for us. And we could, let's see if we came halfway in between, that would be 2, this would be 1, this would be 3. So this again is just a picture of the bottom of our rectangles. We have 8 rectangles. There's area 1, there's area 2, and so forth. I'm not going to label them all. But our heights come from the midpoints. So height 1 comes from that input value. Height 2 comes from there, height 3 comes from there. All right, so there's all the players that I need in order to approximate this area. So area is approximately, what are our widths? Our widths are all the same. It's the right endpoint minus the left endpoint divided by the number of rectangles. So all of the widths are 1/2. The heights, here's the first height. It is the distance between 0 and 1/2 plugged into our function. That's where the height's going to come from. So that is 1/4 cubed. There's our first height. Our second height, if this is 1/4, 2/4, is 3/4. Again, plugged into our function. Our rectangles have to intersect our function. 4/4, 5/4, plugged into our function. 6/4, 7/4. I think we begin to see a pattern. The next one should be 9/4, right? The next one would be 11/4 and 13/4 plugged into our function, and 15/4 plugged into our function. So there we go. We did get it done by the end of the video. So hopefully you can kind of see that you really don't even need a picture, but I would draw the bottom of your rectangles. That is really, really going to help you find where you need to be according to your left endpoint, right endpoint, or midpoint heights that you're going to get when you have those number of rectangles and you know you're dealing with the x-axis and those values. All right, so come to class next time prepared to do some area problems.